Okay, welcome to Geometry, Arithmetic, and Differential Equations of Periods seminar. So today, Masha Vlasenko from INPA, Warsaw, is going to talk about Frobenius constants of differential equations. Masha, go ahead.
Hello, everyone. Thank you very much for inviting me to this seminar. I will speak about Frobenius constants. This is not a well-known term, so first I will introduce them. And I will speak about my recent joint work with Spencer Bloch, where we introduce these constants and study them. But the work is based on previous work of other people, where these numbers were arising naturally, just we gave them this name. And actually there will be periods in this talk, because Frobenius constants are periods for Picard Fuchs differential equations. I will speak about it from time to time. This was the motivation for our work. So let me start. So first I'm going to tell you what Frobenius constants are and give some examples. To introduce them, I need to explain what are Frobenius solutions. I will be speaking about ordinary linear differential equations. So in one variable, like this one. Do you see my pointer?
I don't see. I don't.
We see only the first slide and no pointer.
No pointer in the slide. That's bad.
Neither the slides. If you change the page, I didn't see the new page.
Wait. Let's sorry. Then let's stop sharing and do it again. Because I need to show you something with the pointer.
That's okay.
Do you see it now?
No. Oh, just a moment.
Yeah, okay, now it is.
Yes, okay.
The error. Okay. So this is an example of a linear differential equation. This is a hypergeometric differential equation, actually. And I want to define Frobenius solutions, describe some Frobenius method of solving differential equation near a regular singular point. So I want to say solve this differential equation near t equals 0. If we try to solve it in power series, let's try to plug a power series into this differential equation. We will turn out that find out that the differential equation is equivalent to this recurrence for the coefficients. This is something that everyone who tried to solve differential equations observes, that differential equations are equivalent to recurrences. And to see why this recurrence corresponds to this differential equation, it is convenient to rewrite it in terms of the derivative t d over dt, which I will call theta. So if we, here you see the same differential operator, but multiplied by t on the left. And then we can rewrite it in terms of theta indeed. And here is the differential operator in terms of theta. So theta acts on power series by multiplying an by n. And t does the shift from an to an minus 1. That's why we have n squared and n minus 1/2 square here. This is equivalent to phi being a solution to this differential operator. And so we find a power series solution. Here, this 1/2 n is the Pohammer symbol. This is the classical hypergeometric function. We don't really need anything specific about it. We see that it's a power series with rational coefficients, and they satisfy this recurrence. Also, looking at the recurrence, we can see that there is a unique power series solution up to rescaling by a constant. This is because if the previous coefficient was 0, then the next one can be non-zero only if this n is 0. So it shows us that the solution should have order 0 in t. It does not vanish at t equals 0. Okay, these are some easy observations that we do about this differential equation. But since it's of order 2, there should be a two-dimensional space of solutions, and we only find one when we look at power series. Apparently, there is another one, which is a logarithmic solution. It's a logarithm of t times the power series that we found out before, plus another power series. And these two span the space of solutions. This effect that we have power series solutions and solutions that are polynomials in the log over power series with coefficients in power series, this is a theorem due to Frobenius from 19th century, that near a regular singular point, we can always find the basis in the space of solutions consisting of power series and logarithms.
Hey, Masha, excuse me for interrupting you.
Yes?
You have a pair of solutions. One of them is a formal series, well, formal converging. Another is logarithmic. But in general, this happens because the characteristic equation has a double root 0, right?
Right, right. I will speak.
And so in general, you would have, if it has, say, two different roots, then you would have two different power exceptions, which would start with some algebraic exponents, roots of this equation.
Yes, exactly. So we will do it on the next slide. Let's do it in general. So if we have a differential operator and we want to solve it near a point which in this slide will be t equals 0. So we speak about solutions locally. Then it's convenient to write it in terms of this derivative theta. I will use it throughout the lecture because theta is convenient to analyze the singularity. So if we rewrite our differential operator like this in terms of theta, then we can define the indicial polynomial. It means substitute t equals 0 in the equation, and it will be a polynomial in theta, but now we change it for a formal variable x. This is called the indicial polynomial at t equals 0. And if we want to do another point, we should use some t minus alpha here for the point alpha and evaluate at the point alpha to get the indicial polynomial at alpha. Okay? Roots of this indicial polynomial are called local exponents. I will call them rho. And then for each root, we have a solution which starts, it's a power series starting at degree 0 times t to the rho. If we look at this power series, then the monodromy around t equals 0 will multiply it by exponent of 2 pi I rho. So if rho is a local exponent, then e to the 2 pi I rho is an eigenvalue of the local monodromy operator near 0. And then we also have a bunch of other solutions, which there will be as many solutions related to rho as the multiplicity of rho. They are written here. So this is always t to the rho times a polynomial in the log of t with coefficients in the power series. All power series here are convergent. They are analytic functions in some neighborhood of 0. And what else can we say? if some of you are experts, you can tell me that I'm ignoring one issue here. This formula written here works if rho plus 1, rho plus 2, and so on are not local exponents. So we should choose for each set of local exponents that differ by integers. That will work only for the maximal one. But I'm going to consistently ignore this issue in my talk. Everything will work for this case, but it's technical. So just assume it doesn't.
So you consider in principle only non-resonance equations, non-resonance.
I can do all equations, but I want to ignore it during the talk.
Okay.
I don't want to tell you what happens if something is resonance, or if you have two local exponents that differ by an integer. I just wanted to remind you for now what are Frobenius solutions, and please look at the screen. The way they are defined here, they are unique. So this is a normalization. This power series solution, it starts in degree t to the rho. We take a0 to be 1, and then the next power series that we find here, they all start in degree 1 or higher. We subtract a multiple of this first series, and in this sense we have really a fixed set of solutions. And this power series, as soon as one knows that such a structure in this space of solutions exists, one can find all these power series by solving some recurrences. Okay, so I don't want to show the proof of this fact. It's an old theorem of Frobenius, but it's important to understand that there is some algebraic structure here, these power series that we can find out by recurrences. And for example, if we start with a differential operator with polynomial coefficients, and all polynomials have rational coefficients, then all power series that enter these Frobenius solutions, they will have rational coefficients. For this reason, they are of interest in elementary and not really elementary number theory. So this way, differential equations produce some interesting sequences of numbers, and I'm going to talk about them. Okay. In the next slide, it's a remark. So if you don't know what mixed Hodge structures are, you can ignore me for a second. I just want to tell why Frobenius solutions are interested from the geometric point of view, why they are interesting in algebraic geometry. So if we solve a differential equation and find this basis in the space of solutions consisting of Frobenius functions, Frobenius solutions, as I just said, they can be power series with rational coefficients, and then we can take their rational linear combinations, and this will be a rational structure in the space of solutions, a subspace over Q, such that when we tensor with C, we get the whole space of solutions. What is the meaning of this rational structure? For geometric differential operators, there is a different rational structure consisting of period integrals or period functions solutions. And these are two different rational structures. So the rational structure coming from the Frobenius basis is the de Rham structure of the limiting mixed Hodge structure. This is the reason why Frobenius solutions are interesting and why we care about them, maybe. But in my talk, we won't use this property directly. It's just a motivation. And let me show you an example.
Masha, sorry once again
Yes?
for interrupting you. I guess Hussein will add some more time for my questions. So this rational structure actually exists because you choose the rational initial conditions for your fundamental system solutions, right?
What are rational conditions?
So you have a special basis. As I understand you, Frobenius solutions are just a special basis which is arranged as a flag in the space of all linear solutions. Yeah. And this flag is, you said that the coefficients are irrational simply because you take the initial values for your recurrent sequences being ones.
There is only one choice here, basically. When you start with that power series solution, say times t to the row, then you normalize it by a constant.
So that's basically the initial condition.
Yeah, these are the initial conditions. Yes.
So this is the rational structure that you are talking about is introduced because you choose special rational, in some sense, initial conditions for your basis.
Yes, one can say so. Yes.
Okay.
Okay. If you ignore local exponents like this t to the row, we can choose them to be by the way, for geometric differential operators, for Picard Fuchs differential operators, local exponents are rational numbers. Row is rational. And then for each row, we have a bunch of solutions, power series and logarithmic solutions, and their rational linear combinations, they will consist of rational power series and powers of log. And this defines some rational subspace inside of the space of solutions.
But all this initially depends on the fact that your initial differential equation of second or, say, higher order is defined over Q, right?
Yes. So let me show this example. Let me show the example. It will be clear in the example, okay? So you see here a so-called elliptic integral, which depends on t. And this is a period function which corresponds to this family of elliptic curves here, Legendre family of elliptic curves. So this function solves a differential equation of order 2. And to see this, you can do the exercise of expanding the integrand in t and integrating. And this way we can find that the result is pi times a power series that appeared on the previous slide. And we call this power series phi 0. So the whole integral is a solution to the same differential equation that was shown on the previous slide as an example. I mean, two slides before. So the period integral here, it belongs to that rational structure of period functions, while this phi 0 belongs to our rational structure consisting of Frobenius solutions and their rational linear combinations. And since the space of solutions is two-dimensional, so let's analyze again this differential operator at t equals 0. The initial equation is here, the leading term. You put t equals 0, and we see that it's theta squared. So the initial equation is x squared. We have a double local exponent 0. And we have two solutions, the power series solution and the logarithmic solution. And here is another period integral. The difference is here we integrate from 1 to infinity, and here from t to 1. One can integrate between roots of this cubic polynomial and infinity, between any two of these 4 points, 0, 1, t, and infinity. These will be period integrals. They span this period structure in the space of solutions. And here we express them through the Frobenius basis at 0. And the numbers that you see here, pi, minus 4i log 2, and I, they are therefore periods of the limiting Hodge structure at t equals 0. Okay. That was my remark. And this remark is about the why Frobenius functions are interesting in geometry. And now, as number theorists, we see that it could be interesting to compare two Frobenius bases from different singularities. if we can express one of them in the other one, what are these numbers? I don't think there is a consistent answer in algebraic geometry at the moment. It's just an interesting question to look at. And we're going to look at this question in a particular...
Excuse me, am I right that you are now trying to evaluate, in some sense, the holonomy operator or the monodromy operator of the corresponding Picard Fuchs equation? So you have a distinguished basis near one singularity. Then you can continue it along any path that avoids singularities, in particular to bring it closer to the other singularity. And then you have the change of basis, which is the monodromy transformation, or holonomic, depending on how you call it. And your question was about the arithmetic nature of those holonomy operators, right?
Yes, yes. And I'm saying that the Frobenius basis, Frobenius solutions, are particularly interesting because they sort of connect rational structures which are limiting Hodge structures.
No, the Frobenius solutions are interesting for one simple reason. If you have a monodromy around a singular point, then this monodromy is a self-map of C, and it has the Jordan structure, which is characterized by invariant flags. So you have eigenspaces corresponding to each eigenvalue, to each indicial root, and then inside each eigenspace with the same indicial root, you have the flag structure. So it's in a sense that's what your basis is, that you start with powers of logarithms. So you are looking for a linear operator which conjugates two families of flags in Cn, right?
Yes, one can say so. And let me continue, because I'm going to speak about the particular case of this situation. So let me finally introduce Frobenius constants. To do that, I need to explain what are reflection points. These are singularities of a certain type. So a regular singular point C of the differential operator L is of reflection type if, so here we take sigma C, the operator of local monodromy around C, acting on some space of solutions near some base point. Here, this is the vector space of solutions. This is the C vector space of the same dimension as the order of the differential operator L. Sigma C is the local monodromy transformation around C. We subtract identity. And if the image is one-dimensional, we say C is of reflection type. What this means in simpler terms, it means that for any solution of L, when it goes around C, it acquires, it adds a multiple of one fixed solution. There is one fixed solution associated with this point C up to rescaling, such that every other solution, the local monodromy acts like this. When any solution goes around this point, it adds a multiple of a distinguished solution, and we call them reflection points. For example, hypergeometric differential operators here of any order, the order I will usually denote by R, and theta is, as usual, t d over dt. They all have a reflection point at t equals 1. You can see from this differential operator that near theta to the r, you have 1 minus t. It shows that the singularities are at 0, infinity, and 1. At 0, the local exponents are beta j. At infinity, they are minus alpha j. And at 1, we have a reflection point. In fact, there is a subspace of solutions of codimension 1, which are analytic at 1. And there is all solutions add a multiple of one distinguished solution when they go around one. The question is which solutions. That's interesting. There is no nice formula for that. Now, Frobenius constants, the object of this talk, they are defined in the case when L has a reflection point. This is the only particular thing we need to define these numbers. For such differential operators, we can do the following. We fix a non-zero solution delta such that it's in the image of the variation of the local monodromy. Sigma c minus identity is called the variation of sigma c. And then for any solution, as we said before, it adds a multiple of delta, and the constant here, it depends on the solution. Now, Frobenius constants, we define them as follows. We take another singularity, call it C prime. We consider the Frobenius solutions, the set of Frobenius solutions near that singularity. We fix a path from C prime to C, to the reflection point. And then we bring Frobenius solutions. We do analytic continuation along this path. And then we see how they change locally around the reflection point here. So the constants such that Frobenius solutions add that fixed solution delta times a constant, these constants will be called Frobenius constants. In this formula, gamma is written to denote the analytic continuation along gamma. And C is from this formula, that we just measure how Frobenius solutions change around the reflection point.
Am I right that what you do is the following? You take the point C, because C is the reflection point. The monodromy operator around this point is determined by only one scalar, which is the Frobenius constant.
Yes.
Now you replace the local monodromy near this point by the holonomy of the path that is conjugate in the fundamental group. And then you get another automorphism of the same linear space, which, because of, should also have only one non-trivial constant when you write its matrix in the Frobenius basis. So you are looking how these constants are depending on the path in the fundamental group, non-trivial paths in the fundamental group based chain to the reflection point.
Sorry, I want to give you the definition because this is a number theory talk. I'm interested in these numbers.
Okay.
You will see what questions I'm trying to ask in the next slides. Just note that, say, when you have a Frobenius basis in the space of solutions, we have a vector of numbers here, as many numbers as the dimension of the space of solutions. Sorry, may I ask you please to mute yourselves because I hear my voice from someone else. It's fine. Okay. So we have a vector of numbers, and the only thing it depends on is, there are two things it depends on. One thing is the path gamma here, the homotopy class of this path gamma. This is clear, but in our examples, it will be something fixed. I'm not going to play with the change in gamma. But also, it depends on the scaling of delta here. If I change delta by a constant, then all my Frobenius constants will be multiplied by this constant, right? So it's a vector in the projective space, I would say. So we have a tuple of numbers, and they are well defined up to simultaneous rescaling by a non-zero constant. Let's look at these numbers in some examples. I claim that for geometric differential operators, we are getting very interesting numbers. So here is our example, which was here from the very beginning. And here, for the direct path between 0 and 1, which is a reflection point, the constants are 1 and 4 log 2. And this shows us, actually, that this linear combination, look, this is, if we make this linear combination, then it will be analytic at t equals 1. It tells us that this, the proof of this fact is to show that this integral is analytic at t equals 1. It's an analytic solution. Let's try to generalize this example a bit. This is hypergeometric of any order R. And again, we take a direct path which goes along the real line from 0 to 1. If we compute these Frobenius constants, here is the formula. It's exp of a power series where you see zeta values of the Riemann zeta function. So when we increase R, we will be able to see as many zeta values as we want as Frobenius constants of this differential operator. And in the next example, it's from the famous proof of irrationality of zeta of 3. In that proof, Roger Apuri uses two sequences of numbers, integers and rational numbers, which approximate zeta of 3 in the following way. He can have control of the denominators of Bn. He does estimates of denominators of Bn such that irrationality follows from this estimate here. But in our terms, from our point of view, what is important is that both sequences An and Bn satisfy the same recurrence relation, which corresponds to this differential operator of order 3. I will call it Apuri's differential operator. They are solutions to recurrences. And if we code them in terms of differential equations, so An is a solution, a power series solution. This is another power series solution, but with the right-hand side. So to consider them as homogeneous solutions, we would pass to a differential operator L times theta minus 1 to kill t here. And for this differential operator, at t equals 0, there are two local exponents, 0 of order 3 and 1. 0 is of multiplicity 3, and 1 is of multiplicity 1. And the two generating the functions in Apuri's proof, they are Frobenius solutions up to a constant 6 here. So if we compute Frobenius constants, in this case, they are 1, 0, minus pi squared over 3. This corresponds to the local exponent 0. And this zeta of 3 over 6 here, it corresponds to Apuri's computation. It shows us that the difference of this power series times zeta of 3 times this power series extends through the closest singularity to 0. So this point C here is a reflection point, and this is the closest singularity to 0. The other singularity is the other root of this quadratic equation. It's much larger. So the thing is that we have two power series solutions of this L tilde, and their linear combination extends through the closest singularity. And which linear combination? This is what the Frobenius constant tells you. And here the Frobenius constant is zeta of 3 over 6. All right. So I hope this was motivating enough to study Frobenius constants as numbers. Like, they can be some interesting numbers. And now I want to make a remark, which is a new point, quite recent point, that appeared in the literature in a paper of Golyshev and Zagir about gamma conjecture and mirror symmetry. They proposed something new. They proposed to consider not only Frobenius solutions, I called them phi rho m, where m was the index between 0 and multiplicity of rho. These are the Frobenius solutions to a differential operator L. But Golyshev and Zagier say that we can go higher and produce an infinite sequence of functions, basically as follows. We multiply L by theta minus rho. Let's multiply one time. Then the multiplicity of rho at the local exponent at t equals 0 increases by 1, and the block of Frobenius solutions, which corresponds to this rho, it increases by 1. We are getting one more Frobenius solution. And this is the next one, the next Frobenius solution. And then we multiply by theta minus rho squared and we are getting the next one, and so on. So basically, we can produce infinitely many functions. They will be solutions to L with the right-hand side, inhomogeneous solutions, or homogeneous solutions to such operators. They are produced in a quite canonical way here. I mean, this produces them in a canonical way, but one can discuss whether this definition is actually natural. That would require some time. I think it's quite natural. So let me explain one more thing. So for a differential operator L, we can introduce the adjoint differential operator. The formula is here. In terms of duality for differential equations or for duality for connections, this represents the dual connection in the sense that there is a pairing between solutions of L and solutions of the adjoint operator. And we say that a reflection point is special if all sigma c invariant solutions of the adjoint are analytic at t equals c. Here, it's a technical thing. I needed to tell you something on the next line, but I have to say that since L adjoint represents the dual connection, their monodromy representations, this will be the dual representation here, and therefore C is also the reflection point for the adjoint differential operator, always. And what we require in this definition, so there will be a codimension 1 subspace of solutions which are in sigma C invariant for the adjoint already, but it can happen that some of them are meromorphic functions at C with some pole. So if we multiply the adjoint on the right by some power of t minus c, we will make this condition to be satisfied. Every reflection point can be made into a special reflection point when we multiply L on the left by a power of t minus c. So this is not a serious condition. This is something about rescaling. It's not really serious. But what it makes to us, it makes some magic. It makes it so that C remains a reflection point of all these operators theta minus rho to the j, L. So we can continue our game of computing Frobenius constants, and we can define higher Frobenius constants. So we take these higher Frobenius functions. We now have infinitely many for every local constant, local exponent rho, and we do the same thing with the same delta here. They all will change by a multiple of delta when we go around the reflection point. So what happened on this slide is that now we have infinite collections of Frobenius constants here. For example, for every hypergeometric differential operator, let me consider gamma to be the direct path from 0 to 1, which is a special reflection point, in fact, for hypergeometric differential operators. And now we have infinitely many Frobenius constants, and they all appear to be expansion coefficients of one function here. This is a meromorphic function, a gamma product. And it encodes all of them because we expand at row to get the respective Frobenius constants for the local exponent row. If we look again at the a priori example, so for this differential operator, we take gamma to be the direct path from 0 to this closest singularity, which is a reflection point. In fact, it's a special reflection point. So again, we have infinite collection of numbers. And in their paper, to which I refer, Golyshev and Zager compute them numerically. In fact, it's very difficult to compute Frobenius constants. Usually they come as limits, as in a priori's example a few slides ago. You need to compute some limits of ratios, of coefficients, of power series. And here they do it only numerically because it's hard. And they find out that the higher Frobenius constants are rational linear combinations of products of zeta values. And at point 11, that we went quite high. I mean, the order of the differential operator was 3. They discover even a multiple zeta value, which is something the geometers don't see why. We don't know the answer exactly why yet, but at least it makes sense to ask the following question. Why these higher Frobenius constants are periods as numbers? This is not clear at all from the way they are constructed and from the way they are computed. So in our work with Spencer, we answered this question for why Frobenius constants of Picard Fuchs differential operators appear to be periods. And so now, yes?
These equalities are conjectures because they are approximated, no?
Yes, so they proved it only up to kappa of 3. This first row is the part of their paper, and this is a numerical experiment.
Okay, thanks.
Yes, yeah. So, but their paper initiates this question to understand Frobenius constants motivically, say, to understand them geometrically for Picard Fuchs differential operators. So we made a first step in this direction, and our main theorem will have a corollary that Frobenius constants are periods. Let me show you the theorem now. So the situation is that we have a differential operator L with a reflection point C. Our other singularity is 0, and gamma is some path between 0 and C. And consider the respective collection of Frobenius constants. Remember that this is well defined up to rescaling by a constant, basically. Then we say that there exists a meromorphic function such that our constants are expansion coefficients. For each local exponent, there is the respective expansion coefficient. Coefficients give us the Frobenius constants. This statement is interesting because imagine that you have a collection for one fixed local exponent. There can be only one, say rho equals 0 if we have maximally unipotent monodromy at 0, the situation of the a priori example. Then we have this infinite collection of numbers. So this theorem says that the respective power series is a meromorphic function. It's a meromorphic continuation theorem. It continues meromorphically to the entire complex plane. But we have more to say. So this function can be given in the following form. So this I here is the indicial polynomial at 0. R is another polynomial of degree at most as the order of L, at most as the order of this indicial polynomial. It's defined as the polynomial of minimal degree such that R of sigma 0 is the monodromy around 0, annihilates the image of sigma c minus I on the solutions of the dual differential operator. So it's a well-defined polynomial. If we call this the image of solution of this image is spanned by some solution delta, as I used this notation in my slides, then R of sigma 0 kills delta. This is again a polynomial. And this here is a generalized gamma function. It's a Weiss generalization of the gamma function. It's a Mellin transform of a solution of the adjoint differential operator along some path, a closed loop. And this definition will make it into entire function. It has no poles. So our formula gives us a control of poles of this function, the generating function of Frobenius constants. Let me show you a few examples of particular cases of this formula. So if you look at the upper raise example, here the generating function of Frobenius constants, well, we have only one local exponent at 0, and we have infinitely many numbers which Golyshev and Zagier computed numerically starting from here, from S to the 4, right? It appears to be a meromorphic function, which can be written like this. This is our initial polynomial, S cubed. This is the polynomial R I was talking about, up to rescaling by 2 pi I cubed. And this is an integral of a solution to the differential operator L. Well, we should consider adjoint, but this operator appears to be self-adjoint. Formally, the adjoint is minus L. So this is a solution to L. And here, there is a loop, which is given explicitly. So it makes 3 times it goes around C, and then around 0, again C, 0, again C, 0, and then again around C, and then it unwinds back around 0. So it's a closed loop, which makes it the function t to the s to have no monodromy around it, because we went as many times in this direction around 0 as many times in the other direction. And psi is, it appears to be that there is a unique sigma invariant solution along this loop. And we normalize it so that the integral here is 1. That defines the right-hand side precisely. And this solution, well, we can give it explicitly as a linear combination of Frobenius basis solutions if we want. But anyway, it's unique. This is what happens in the Golyshev-Zagier example. And now the corollary of our theorem is, as I promised, that for Picard Fuchs differential operators, the Frobenius constants are periods up to some powers of 2 pi I. And the reason is this. So our formula expresses Frobenius constants as Q bar in general, linear combinations. Q bar comes from the fact that well, the Picard Fuchs operator can have coefficients in some algebraic number field. So I will have coefficients in Q bar. And the monodromy representation will be defined over some number field. Or actually, it's defined over Q. Okay, so this R will have coefficients in Q. So they are Q bar linear combinations of the derivatives of the gamma function and some powers of 2 pi I coming from here. And the derivatives of this generalized gamma function, they appear to be periods. And here is the reason. So if we have a formula like that, and we differentiate it m times, then we are getting log t to the m here. And this appears to be a period integral whenever psi is a period function, which happens to be so. And local exponents are rational numbers. So this is algebraic here. This is the idea why they are periods. And I didn't say it in the main theorem, not to overload that slide, but our generalized gamma functions, they are constructed using some rational structure in the space of solutions, if we have it. So for Picard Fuchs differential operator, the solutions showing up here in the Mellin transform, they will be period functions in the main theorem. That's why the corollary makes sense. The corollary is true. Okay, and just a few words about the gamma functions, the generalized gamma functions that enter the main theorem. So for a differential operator on the Riemann sphere minus finitely many points, we can consider such functions as before, where we have a solution to L here, and we integrate along a closed loop here, and we choose the loop so that t to the s has no monodromy along this loop. And psi is a solution which has no monodromy along this loop. So the integral is well defined. You can break the loop at any point, parameterize, and compute the integral. And it's so well defined that it makes sense for any number s here. So it's actually an entire function. We attach to the differential operator a bunch of entire functions. Well, it's infinitely many entire functions, but let's see how many. One can generalize this definition a bit. In fact, one can consider sort of linear combinations. And our gamma functions are defined using symbols in homology, in the first homology of the local systems of solutions to L, tensored with the rank 1 local system generated by t to the s. Well, what you see here are just solutions times t to the s, and they are coupled to loops in a way that, I mean, the thing that the symbol is in homology makes this sum to be well defined, as before we had a closed loop and invariant things, so that everything is well defined. Let's just skip the details, but we can consider such gamma functions. They are all entire functions, and they form a module over Laurent polynomials of e to the power 2 pi I s. Just as you see them, e to the 2 pi I s appearing here. You can multiply by e to the power 2 pi I s. And it's always a finitely generated module. So there are finitely many interesting gamma functions, and all other gamma functions are e to the 2 pi I s linear combinations of those interesting functions. Now, let's go back to the situation of Frobenius constants, to the situation of our main theorem, when we have a singularity at 0 and a reflection point singularity at c. Well, I don't assume it to be a reflection point for the moment, just two singularities, 0 and c, and some path going in between. Take a neighborhood of this path in the analytic topology and compute this number. This is the dimension of the image of the variation of the monodromy around C. For example, if this is a reflection point, then this D will be 1. But in general, there is some dimension of the image of the variation, rank of the variation of the local monodromy at C. Then the respective module of gamma functions, which are supported in this neighborhood. So it means that we are taking loops of integration belonging to this neighborhood of the path. Then this module of gamma function is generated by at most d elements. In particular, for the reflection point, we have one interesting gamma function in our situation, something which is defined around this path. And this is the gamma function in the main theorem. Okay. Now, I think I will stop. I will not show you the proof, but if someone is interested, we can do it during the discussion. So let me skip a few slides with the proof, and thank you.
Okay, thank you. Okay, thank you, Masha. So any question? Well, Masha, maybe I have one question. The most famous Picard Fuchs equation that comes from physics, this mirror quintic, Gauss hypergeometric function, 1/5, 2/5, 3/5. So the structure of this Frobenius constant in this case, it's also we know it, or how it is?
Well, we had a slide answering this question in general for hypergeometric differential operators. We will make some gamma product, right? Gamma of s plus 1/5, s plus 2/5, and so on. Divide s plus 4/5. We will divide it by some gamma of s, more or less like that. And then maybe we will use the formula for the gamma product with the shifts on the top. And I think in the end, we will get linear combinations of products of zeta values as Frobenius constants. And it will follow from this formula that I showed in general for the hypergeometric differential operators. I just want to add to this that hypergeometric case is the only case where we can compute all Frobenius constants explicitly. That's the only known case where they can be computed, actually. Everything else seems too hard for the moment. Like you have seen that Golishev and Zagier have an operator which is not hypergeometric. It corresponds to a recurrence of longer recurrence, a bit longer. And they already compute only numerically.
Okay, but still we expect that in this zeta values.
What makes it interesting that there are multiple zeta values.
Multiple.
Hypergeometric can make any zeta values here, but multiple zeta values seems to be mysterious, I would say, in that case.
Okay, I think we have some echo problem. If somebody wants to ask question, turn off the microphone. And okay, any other question?
Yes, Masha, I followed with great interest in the first half of your talk, which was analytics. So I had an impression that I understand everything. Once you switch to the number theoretic things, I almost completely lost. I'm not a number theorist. But I have a stupid question, the most naive one. What could you expect from studying this type of questions? So what kind of advance that would be interesting for the number theorists? Thanks, and I switch.
Okay, I think the main question that drives this is the one I said where you were still following. So if we take two singularities and compute the connection matrix, you had a different name for it, but I forgot, monodromy holonomy matrix, in the pair of Frobenius bases. That will compare two rational structures coming from different singularities. This is something which arithmetic geometry might not understand well yet, the comparison of two limiting mixed Hodge structures.
Well, I would probably say it as follows. You have actually three rational structures. One comes from the fact that your initial equation was defined over the field of rationals. Without this, I guess that everything ruins down. Then you have two rational structures which come both independently from each singularity. And actually, the question is not about the two, but about the three rational structures. One of them being fixed because you kind of fix the equation, but still then the question was a sort of informal. So would you expect that, say, a rationality or irrationality of zeta values be proved this way? Or would you expect that, Manin, not Manin, Kontsevich and Zagir wrote many years ago a famous preprint that was never published, as far as I know, which was called Periods. And then there is
published. Yeah,
it was published.
Yes, I liked it a lot, as many people do, and it was published. Yeah, but sorry.
Okay, but in any case, the preprint is as almost everything that Kontsevich writes is kind of inspirational, but still there are no accurately formulated conjectures of what you could expect from the relationship between periods, number theory, and so on. So you are clearly working much closer to this area of number theory. So I would like to hear your first-hand opinion. So how it would advance the number theory?
I think that knowledge that something is a Frobenius constant doesn't really give a proof of irrationality. People tried to generalize a priori proof, and there was no success yet. But we know I told you that higher zeta values appear as Frobenius constants of hypergeometric differential equations, for example. So the knowledge that some zeta value is a period gives us nothing, basically. We know that already. All zeta values are periods in the sense of Kontsevich-Zagir and in all more advanced senses, some period of mixed motives, if I remember that correctly. So I don't think we are going into the direction of irrationality proofs here. But the question which interests me, so I started with this example of the Legendre family, or the hypergeometric differential equation of order 2 with constants with the parameters 1/2, 1/2, and 1, the very beginning. This corresponds to a family of elliptic curves. And now we compute Frobenius constants, and they appear to be some zeta products of zeta values, basically. Why is that? We don't know. For hypergeometric differential equations, we have some formal answer. We can compute them. But I don't know how geometrically these numbers are attached to the family. I mean, what we can say is our theorem that I told you today. We can construct some Motivic gamma function, some generalized gamma function, which generalizes the hypergeometric example very far. And some derivatives of this function will be period integrals that represent these Frobenius constants. But that doesn't give us much understanding of their structure as numbers, actually. So the question we are solving is we are trying to do the geometric construction of Frobenius constants, starting from the basic family, say from the family of elliptic curves that corresponds to this differential equation. How would you go to Frobenius constants? What are they? Which period integrals are they?
Okay.
Hussein, maybe
I will stop our recording first, just here, and we go to the informal.
As you